In today's episode of Machining and Microwaves, there'll be a bit of and plenty of plus some bleep bloop computering as I show you how to design, model and machine a high performance antenna feed for an X-band parabolic dish and use it to reflect microwave signals off the moon and deliver optimal performance with satellite and terrestrial communications. As usual, my artificially intelligent machining and engineering expert AIMEE will highlight my mistakes, failures and shortcomings.
There are just so many to choose from.
So helpful. The design's inspired by a Feedhorn construction first shown by Jeffrey Pawlan in Dubus magazine. It's a brilliant read. Subscription info's in the description. Jeffrey's design's based on the Pickett-Potter horn first described in the 1960s, with some neat tricks to allow it to be fed by a convenient standard rectangular waveguide. The design has three parts: an oval iris, a round waveguide phasing section and a flared conical horn. I'll be making this one from aluminium, or aluminum for those from countries which have successfully sent folks to the moon. Here's two I made earlier to Jeffrey's original designs. My feed horn design has different dimensions. The transition phasing section and horn are calculated for a deeper dish with a shorter focal length than Jeffrey's feed horns. We need to illuminate as much of the dish as possible, but not at the expense of excessive overspill around the edges of the dish. A parabolic dish focuses any ray from infinity that's travelling parallel to its axis down to a single point at the focus. It also works in reverse, so a signal generated at the focus will be sent out in a searchlight type beam from the surface of the dish. The required angle is around 112 degrees. I'm aiming to produce a beam pattern with a flattish peak that drops rapidly beyond the edge. Now it's time to leave the familiar mechanical world of 3D CAD and step into the world of time domain electromagnetic modelling so we can optimise the feed horn dimensions to generate the best possible radiation pattern for our FD.5 dish. We need to create a model of the feed horn and define the materials it's made of, and then set up a 3D mesh of cubes. The program then calculates Maxwell's equations for every cell, looking at the electromagnetic fields to each face of the cube and iterating over tens of thousands of steps to work out how the fields in every cell change over time. The results are then used to calculate the far-field radiation pattern generated by the fields within the feed horn. Right, time to cut some metal. This is a bit of 2¼ inch 6082, which I'll face off and machine to 0.5 mm over size. That'll allow me to take a finish cut to 52.0 mm with the three parts of the horn assembled. I'm using my trusty Pratt Bernard 200mm 3 jaw. I reground the jaws a while ago and it centres very accurately. The insert's a high rake polished CCGT 120408 with a 0.8 mm corner radius. The chip breaker on these needs the nose to be buried deep and some pretty optimistic feed rates, so I'm expecting a lot of stringy chips as I'm only taking light cuts. This batch of 6082 seems to be very gummy and needs a very sharp tool, and this insert's a bit tired, so the finish isn't going to be exactly stellar. I turned the insert round and it's 78.35% better now. A quick check of the OD shows I'm still 0.4 mm oversized, so I'll take the usual 2 balanced cuts to get to the final size. It doesn't really matter, but a bit of unnecessary precision brightens the day and makes me think I'm not totally rubbish at machining.
It's just beginner's luck.
Ooh, I never noticed this before, but here's a Back to the Future moment. Is that logo on my Tesomite really from the DeLorean Motor Company? Collector's item. The next stop's drilling and reaming a reference hole in the centre of the section that'll have the oval iris. A split point stub drill would cut this perfectly concentric, but I'm a creature of habit and I used a centre drill, not even a proper carbide spotting drill. Don't at me, bro. The drill's a 7.5mm stub-length cobalt high-speed steel split point that I got from the most excellent drill service of Hawley. # not sponsored. Now I could use the OD as the reference, but I'm planning ahead here, and I've got visions of aligning the oval iris plate on the rotary table with a gauge pin or an indicator in the central hole. Reaming the hole's probably overkill, but if a thing's worth doing, it's worth overdoing. I'm parting this off a little oversized so I can use the British standard eyeball precision alignment technique and wind the carriage along a bit using the DRO to move exactly 10-ish millimetres. For cutting edge engineering fans, that's 3/8 of a banana. Ooh, that's a bit squeaky.
You didn't check the edge on that parting blade insert, did you, Neil? It's dull as a dull thing. A bit like you.
Before AIMEE yells at me, I was simply seating the insert correctly in the holder using a soft-faced dead-blow hammer. Any scurrilous allegations about me bashing the delicate carbide on a slab of steel in a fit of pique are wildly exaggerated. The new insert's right biased, so it leaves the pip on the stock rather than the workpiece. It's a 2mm Corloy SP200R from Cutwell. It certainly seems to be breaking chips very well. And Mahjong. Am I doing this right? The next step's the phasing section. I'll face it off square and then drill and bore it out to final size at 26.0mm and part it off. There's something a bit rubbish about the grind on this 21.5mm drill. It skipped off to one side and then recentered itself and now it's wobbling. Not impressed.
Whee! Did you grind that drill yourself?
No, AIMEE, I didn't grind it. I bought it. It was cheap.
It shows.
This 1-inch blacksmith drill's great for hogging out loads of metal. I should have used it in place of the 21.5. Now I need to bore it to 26.0mm to form the circular waveguide phasing section. This bore along with the step helped to excite a second waveguide mode in the horn section. I'll start by touching off the tool on the face and zeroing the DRO y-axis. The linear polarised transverse electric mode from the rectangular guide then gets superimposed onto the second mode. The length and taper of the horn are calculated so the two modes, which have different phase velocities inside the horn, arrive at the orifice in phase. The effect's to create a very clean antenna radiation pattern with near perfect axial ratio and very well suppressed side lobes. Which is a good thing. Hey, perhaps I should make a second channel to do deep dives into the tech explanations without upsetting the almighty YouTube algorithm. Things that make you go, Let's see if I'm close to the finished size. 315 micrometers to go. The DRO alleges that to be the case, but I don't trust the digicals.
Never trust anything that has an API.
AIMEE, I do believe you're blushing. Because I'm feeling overconfident, I took that as a single pass. Let's see if I messed up. AIMEE, not one word please. I think that'll do. This time I'm taking a lot more care to get the parting tool aligned with the edge of the workpiece. I'm using the edge of a ruler and feeling for that little click as I move the carriage. I haven't been able to find right biased inserts for this MGMN parting tool. As you can see, it's left behind a bit of a burr. Okay, a lot of a burr. The next stop's facing off the inner end of the main horn. I'd be endlessly grateful if you would click the like button, and if you subscribed, my life would be complete. That finish isn't quite as good as I expected because I ran it at the wrong speed, so I'll take another cut at the right speed. Now that's way better. To get the best possible precision when cutting the horn taper, I'm machining a parallel bore of the exact size of the smallest diameter. Then I'll be able to use the compound to cut the precise angle, taking a finish pass that almost reaches the face. It's critical that the small end of the bore is concentric with the phasing section. The open end also needs to be reasonably concentric of course, but micrometer precision isn't really necessary. So that's 0.57mm left to go. I'll take it in 2 passes. I think it's fair to say that that'll do.
What about the 2 other parts you had to scrap?
AIMEE, I thought your user manual said you always told the truth. I'm shocked. Have you been talking to that ChatGPT again? Now it's time for a bit of trigonometry. I need to set the compound to 4.17 degrees, so I'm using the DRO to measure y-axis movement of the carriage and an indicator to show the corresponding x-axis movement of the edge of the compound relative to the lathe bed. I'm making some assumptions about the collinearity of the compound sliding the edge of the body, but I've checked it previously and it was very precise. Don't know why I sound surprised about that. This old cast iron clunker was made back in the day when lathes were lathes. I'm aiming for about 100mm of travel, and that should get me about 8mm of travel on the indicator. The calculation's nice and simple. Starting from the half angle being 4.17 degrees, I calculate the tangent and get about 0.0729. If the x-axis travels 8mm, the y-axis needs to move 8 divided by 0.0729, or about 109.74mm. That's a bit inconveniently long, so I'll drop it a bit and use a 7mm X travel, which corresponds to 96.01mm on the y-axis. Tolerance on the angles plus or minus 0.02 degrees, so anything between 4.15 and 4.19 degrees is acceptable. That gives a Y range of 95.6 to 96.5 millimeters for a 7mm x-axis change. After a lot of tweaking and tappy tap tap, on the 4th attempt, this happened. "96.105 is very comfortably within the tolerance range, so I think it'll do." I started taking shallow cuts to avoid chatter and moved the cross slide out 0.5mm at a time to take 250 micrometer depths of cut. I'm cutting the taper from small to large diameter so I can see exactly when I hit the edge of the parallel bore. Leaving the workpiece on the original stock maintains concentricity perfectly. The slight extra fiddliness of cutting a blind outward taper is a small price to pay. The next stop's machining the reduced OD of the horn. I'll leave the OD 0.5mm over size and not finish the 45-degree chamfer completely. I'm using a narrow high rake insert and plunging in the start of each cut. I'll part off the horn a little over long and cut it precisely after mounting it on a fixture, measuring the taper length with a depth micrometer. This could have been planned. I even chucked up the stock with enough spare length so the parting tool won't foul the chuck jaws. Way too professional. With a workpiece as delicate as this, I'd usually put a soft rod into the tailstock and insert it into the bore to catch the part as it falls, but this time I'm saving milliseconds by using the handle of the brush that I'm adding lube with. It's easy enough to add a dab of lube and still get the handle back in time to catch the... Oh.
Oops, butterfingers.
Remarkably, the workpiece is entirely unharmed despite my total fumbling incompetence. It's time to deploy one of my favourite tools, the Edge Precision Chuck Stop Set. It lets me align parts with a rear reference face in 3-jaw chucks more than 6 inches diameter. Mine's an 8-inch, so it's perfect. It holds 3 precision parallels against the chuck face and the body has 3 magnets on it, so it's easy to fit. The kit comes with 10 sets of parallels and various alignment plugs. Links in the description. This is a tool I use a lot. If you're sneaky, you might be able to buy a spare carrier and spare parallel set, but I paid for a full set. Hashtag not sponsored. I do get a small commission for any purchases through the Amazon links at no extra cost to you. The Edge Chuck Stop Set usually provides excellent alignment, but I'm in paranoid mode and I decided to check everything. That's perfectly fine for trimming to length. The tolerance on the horn length's about 0.05mm, so the calipers would be fine. I could use the DRO to set a datum at the face of the parallels and cut to the indicated depth, but I'm in the mood to use calipers just this once. Let's see how badly I can fail. I need to remove another 1.76 millimeters. Right, there's a little over 0.5 millimeter to go, so I'll take 2 cuts of about half that and see how we get on. Right, the moment of truth. Have I hit the tolerance?
The precision of those cheap calipers way exceeds their accuracy. Not bad though, for a lame attempt by a fumbling bodger.
And that, my friends, will definitely do. It's oval iris time, or thickness of oval iris time anyway. The tolerance on the thicknesses of the oval iris and phasing section are pretty tight at 0.02 millimeters, and the parallelism needs to be good to 0.04 millimeters.
Bit of a bird's nest there. Sweet.
I'm within 0.4 millimeters of the finished thickness now. The last cut was 0.2 millimeters, so the tool pressure and deflection should be the same if I take another 0.2 and then remeasure and take a final cut of about the same depth. A lot depends on how level the edge chuck stop is. I stone the face of the chuck now and then, and off camera I ran a 2 micrometer resolution dial test indicator over a very flat test disc which is lapped carefully parallel. Given the tolerances I'm working to, it's probably a bit silly, but I just like things to be right. I'll follow a very similar process to machine the round waveguide phasing section to thickness. Right, let's see if the phasing section's within tolerance.
Before you get overconfident, how about checking it on the opposite side?
Just for once, AIMEE, I'm way ahead of you. And I'm pretty sure that'll do. Right, that's the main lathe operations completed. The only remaining turning ops, the final OD finish and some polishing of the inside of the horn taper. Next machining stage is milling the oval iris on the Bridgeport using my 8-inch rotary table and then making the clearance and threaded holes. That'll all be in part 2, which will be up there soon. YouTube thinks you'll like that one too. Please subscribe if only to make AIMEE happy.